In this video, we're going to look at the hydrology that creates a sabkha and controls the textures and the thicknesses of the various units in the sabkha. We are dealing with a depositional system that is part of an overall general set of evaporite principles and controls, and they're all predicated on the observation and the fact that evaporites are hydrogeochemical sediments. This means that the hydrology in the depositional setting and the consequent diagenetic textural overprints are related to hydrology and the evolution of that hydrology, as is the brine geochemistry and the various minerals that precipitate both depositionally and diagenetically from that brine geochemistry in the depositional setting and in the consequent diagenetic environment. So, what do we mean by the term sabkha? Well, in terms of semantics, sabkha, the word sabkha, is a transliteration from the Arabic sabkha or sabkha, and it's describing any salt marsh, any area of extensive, barren, salt-encrusted, periodically flooded, coastal or inland mudflat. Geologically, I like to use the term sabkha to imply intrasediment growth within or around the capillary fringe, which is centered on the water table. So, in terms of fairly strict geological usage of the term sabkha, it implies, both in continental and marine settings, intrasediment growth of salts within the capillary zone, typically in a capillary zone that's less than a metre thick and that's capped by some sort of deflation lag or deflationary surface. So sabkha is part of an overall evaporite hydrology within the depositional system. The sabkha tends to be what we can think of as a saline edge hydrology, passing into the saline pan, which is characterized by the coming and the going of thin brine sheets, and then out into the more perennial brine-covered sump region, where we have predominantly subaqueous evaporite accumulations. And we talked about this style and the importance of heliothermy and meromixis versus holomixis in a couple of earlier modules. So basically, if we do a transect from the margin into the perennial center, transition from the sabkha environment around the saline edge across the ephemeral mudflat system, and then out into the slightly deeper perennial zone of permanent hypersaline brines. The important thing to remember in the terms of what we're describing today is that sabkhas tend to define the saline edge in both continental and marine settings. Now, the term sabkha, because it was derived in the region of the Al Taf or the Abu Dhabi coastal zone, does have implications in the minds of many geologists that it's a somewhat unique system. In my mind, it isn't. It's just merely part of a more general salt-flat capillary zone hydrology. But if we focus in on the classic sabkha sequence, and there's Doug Shearman from Imperial College taken in a photograph in the early 60s, and this is when much of the original work was done by Doug and his various PhD students looking at the supratidal zone in the sabkha. They defined the classic sabkha succession. It consists of a peritidal association with, at the base of the sequence, lower intertidal and lagoonal muddy, often serithid-rich pilloidal sands, overlain by an intertidal zone dominated by various microbial matte textures, and that in turn is overlain by the supratidal zone, where we find the characteristic evaporites accumulating. Now, the evaporites in a sabkha succession are at a maximum in the zone immediately above the water table. The water table position here is defined by that red line. Above the water table, we have anhydrite accumulating. Below the water table, we have gypsum accumulating. Above the water table, gypsum can also be present, but anhydrite is never present below the water table in a sabkha succession. The other interesting thing to note here is that the evaporite accumulations, the white cottage cheese, in this case mostly anhydrite nodules, are found focused in a zone immediately above the water table, and this, as we shall see, is the capillary zone. Notice the 1 meter scale there at the top of that image. So that's the classic peritidal sabkha succession, and in it are growing characteristic anhydrite nodules. Now, around the water table, the anhydrite nodules have the consistency of cottage cheese. As you move to the upper parts of the supratidal Sabkha succession, the anhydrite tends to become a little harder. Still break it open with your hands, but a little harder, a little more brittle within the matrix, which can be carbonate toward the marine side and aeolian toward the continental side of this prograding supratidal zone in the Abu Dhabi Sabkha. So that's the classical vertical sequence in a Sabkha. And notice that the supratidal zone is less than about a metre thicker. That'll become significant as we discuss the capillary zone extent in a few slides' time. So let's have a look at the actual growth form of a Sabkha anhydrite nodule. And this comes from work done by Doug Shearman and Fuller back in the 80s, where they looked at a range of Sabkha nodules, modern and ancient, and how the nodule actually grew. And they came to the conclusion that Sabkha nodules grow displacively as a succession of lathes drive inside-out nodule expansion. And the two dominant styles of anhydrite that we see within the Sabkha matrix sediments are either enterolithic or a more massive development where the edges of the Sabkha define what Shearman and others have called a chicken wire texture. In terms of the actual growth mechanism, there's a pretty consistent observation that when you look at the texture in an anhydrite nodule, both modern and ancient, we see subparallel lathe alignment on the nodule margin. As we go within the nodule, we see a range of decussate and old parallel arrangements, and what Shearman and Fuller concluded in a benchmark paper back in 1989 was that the lathes are growing successively, and as they grow, they break. And so later lathes break earlier lathes. The black arrows there are showing the positions of growth of a new lathe going from left to right. And you can see that as that happens, the lathes tend to rotate into more aligned positions around the edge of the nodule. And we can see that in a whole range of Sabkha nodules. These are Triassic nodules from evaporites in the UK, but we see that same consistent form in anhydrite nodules with parallel to the edge alignment and then a more decussate central zone in the Sabkha, indicating, as Shearman concluded, that the nodules are growing displacively by expansion from the inner to the outer edge of any Sabkha nodule. So this is telling us that there has to be a hydrology where the anhydrite is growing that is saturated with respect to calcium sulfate. And as we saw earlier, that zone of saturation tends to lie above the water table, and that is what is known as the zone of capillarity. So let's look for a moment, what is capillarity? And we think of capillarity, remember back to Physics 101, with a simple statement: the smaller you are, the higher you can rise. And of course what we're talking about is pore throat diameter. So what's happening in any capillary rise hydrology is that we have two effects acting in opposition. We have surface tension versus the forces of adhesion. So as we discussed in an earlier module, surface tension tends to hold any water surface intact. It's due to the polarity and the intermolecular attraction. And so of course this will create a curved meniscus at any pore water contact. But we also have the forces, the adhesive forces, which are causing the water to be attracted to the surface. In this case, we're looking at glass tubes in the diagram on the right, but it could also be in terms of pore throat edges, the solid matrix. And so capillary rise is occurring when the adhesion to whatever the surface we're looking at is stronger than the cohesive surface tension forces between the water molecules. And so we get the effect of that in what we term capillary wicking. This is occurring where the pore water and the inner pore wall interact, and the adhesive forces tend to pull the liquid contact up the column, and the surface tension forces tend to contract it and pull it down. And so those two forces will interact until they reach a balance. And that balance is what we call capillary wicking. And so for water, the narrower the diameter of the pore throat, the higher will be the capillary wicking or the capillary rise. The larger the diameter of the pore throat, the less the degree of capillary wicking. In some other liquids, like mercury, we see negative effects related to the very strong cohesive forces present in mercury compared to water. So Here's a simple experiment which confirms the effect of capillary wicking. What we can see is that with successively narrower pore throat diameters, the level of capillary rise is greater. Now here we can see it in a quite simple experiment with blue dye stained water being poured into a set of capillary tubes of varying diameters. And quite clearly you can see that the narrower diameter tube shows the higher degree or the higher elevation of capillary wicking or capillary rise. And there is a very simple equation for that, where the capillary pressure, P subscript C, is equivalent to the pressure of air minus the pressure in water, or delta P, and that's related via the very simple formula to sigma cos theta divided by the radius of the tube, where theta is the contact angle, indicative of the adhesive forces, and sigma is the interfacial tension, indicative of the forces of surface tension attraction. So let's have a look at the implications of that very simple set of observations from Physics 101 experiment into salt flat and Sabkha associations. And to do that, we'll go a study that was done back in the mid-90s, looking at the sand flats and the salt flats in the saline Owens Lake of California. So you can see that Owens Lake is made up of a succession of three basic depositional settings: a perennial brine pool, a extensive saline mudflat, surrounded by a sand flat. And if we look at the measurements made, we can clearly see that rates of evaporation in millimeters per day are much greater where we have free surface water than where we have any sort of saline mudflat or sand flat. Notice that we have the well B1 located in the sand flat and the well B2 located in the clay dominant saline mudflat. So when we look at the capillary profiles in this salt flat, and this is true of any salt flat around the world, and you'll see similar things, where in the sand dominated system we have a relationship where this is above the water table. If we're at the water table, the volumetric water content would be 1, so we're a little bit above the water table in the zone, the vadose zone, and the zone of capillary rise. And you can see that the chloride concentration in the sand flat above the water table does not change substantially until we get to about 50 centimeters below the land surface, and then we see a significant change in the chloride concentration and also a significant decrease in the volumetric water content. If we do the same thing now in the saline mudflat, well B2, we can see a similar profile, except that now we have a much more linear increase in the chloride concentration as we move up through the vadose zone above the water table. But once again, we see the same thing. It's only in the uppermost 10 to 20 centimeters that we see really high concentrations, upwards of 150,000 milligrams per kilogram. At the same time, you can see that the volumetric water content in the saline clay-dominated mudflat is a little higher than in the sand flat. But it too does not really lose significant volumes of the water content until we get to the upper 10 to 20 centimeters below the surface. So what we can say that for both the more sandy profile and for the clay-rich profile is that salinity of the residual brines increases significantly only very shallow below the surface. And this, if we have capillary evaporation, would be where we would find the precipitation of most of the salts in the system. Now there is a conflict here. If you think back to where the salts sat in the Sabkha, they were not directly below the surface. The anhydrite was focusing around the water table with gypsum below and a mixture of gypsum and anhydrite above the water table in that Sabkha profile. This is not the sort of evaporite profile that one would expect if we have just purely capillary prograde precipitation of salts. And we'll come back to this notion of retrograde versus prograde precipitation of salts in a Sabkha a little later in this module. However, what this is also showing us is that water is being lost from the uppermost part of this profile. And as that water is being lost from the upper 10, 20 centimetres, water is moving upwards via capillary wicking, which is why we're maintaining volumetric water contents of 0.6, 0.7 in the vadose zone, in the capillary zone, above the water table in both these profiles. So this profile in the sandy flat and in the saline clay-rich flat are telling us the same thing, that there is capillary wicking going on and that water is moving up from the water table up toward the surface where it's being lost. And so this is the process of capillary evaporation, with maximum water loss occurring in the uppermost few centimetres below the surface. So it's the heating of the pore waters that's moving the liquid into vapour, which is then leaking into the atmosphere in the uppermost part of this system, and then that water that's being lost by evaporation is being replaced in that uppermost portion by a capillary rise from the water table up into that uppermost zone. So that's the process of capillary rise in action, and it's visible in these moisture content and chlorine concentration profiles in the mudflats and the sandflats of Owen Lake. And there's another process that we have to think about in any salt flat and Sabkha succession, and that is wind action, or the superposition quite often in these arid and semi-arid saline mudflats and Sabkhas of what is known as a Stokes surface. What do we mean by a Stokes surface? Well, Stokes surfaces are related to aeolian erosion. So, if you ever stand on a sand dune, this is what you see. Siltation, deflation, sediment moving around on the dunes. But there's another process here that one should think about that's related to the derivation of these sands that are moving around on the dunes. And that is that sand has to come from somewhere. Ultimately, we are deflating a region and then accumulating sand in dunes. And it's that deflating region, that flat, extensive area between the dunes, which is a deflation surface, which is allowing sediment to move from the low areas between the dunes into the dune systems. And that area of deflation or erosion is what creates a Stokes surface. So we have movement of sediment, and as that loosely bound sediment is being blown around by the wind, within that system we will also have a water table. Below the water table, that sediment will be resistive to deflation because it's water wet and it will cling, and so we won't see a lot of erosion. Above the water table, we'll see aeolian dune migration, we'll see migration of sediment. Now what a Stokes surface is a deflation surface which defines the top of the wicking zone or the capillary zone above the water table. So a Stokes surface is the top of the zone where there is sufficient moisture to prevent deflation. Above the top of the Stokes surface, sediment is eroded and blown away. So we can think of a Stokes surface as a bounding surface that we see preserved in many aeolian systems. A Stokes surface is what also controls uppermost position of the Sabkha sediments. So here's a general hydrological profile in any system. We go from the phreatic or saturated zone, where we have 100% water saturation below the water table, and then above the water table we go through the zone of capillary wicking or the capillary fringe, and at the top of that zone there is a zone where we have a drop in the moisture distribution, so that now the sediments are potentially susceptible to deflation. Of course, this will depend on whether we have a grading water table, a stable water table, or a falling water table, where that Stokes surface position will be. But anything sitting above the top of the capillary fringe, we have a situation where we have the potential for deflation. And as I said, that capillarity zone above the water table is where the evaporites are forming in any salt flat, saline salt flat, or Sabkha succession. So, in a single concept, we can explain the Sabkha succession, and that is capillarity above a water table will define the thickness, the mineralogy, and the textures we see in a Sabkha succession. A Sabkha succession is just another name for a salt flat. So let's talk about it in terms of capillary salt flats, and we'll just have a look at a few now to get some indication of the commonalities that we see related to salt flat or Sabkha sedimentation in both marine margin and continental associations. So this is showing us the distribution of some of the various saline salt flats or Sabkha successions in the Holocene from around the world. And of course the commonality here is they're all forming in regions with relatively shallow water tables, both in the marine margin setting and in the continental interior setting. And this is superimposed on a Köppen climate map. And you can see that the majority of these saline mudflats sit in the browns, which are the arid to semi-arid desert belts north and south of the equator. So if we quantify that now and put it onto a plot, on the left hand we are looking at latitude north and south of the equator versus area of these saline salt flats or sabkhas. And on the right we're looking at elevation above mean sea level. And we've superimposed on that the arid climatic belts of the system. So in the Köppen climate system, B means arid. And we either have hot arid deserts or somewhat less arid but steppe-like climates, arid steppe climates, BS environments, or cold, BWK and BSK, cooler desert belts. But the commonality to all of these Sabkha associations, be they in the very hot and hyper-arid systems down to the more steppe-like arid belts of the world, is that they are indications of relatively shallow saline water tables and capillary evaporation. So let's have a look now at a few examples. So here we are in the empty quarter of Saudi Arabia, and within that succession we can see a zone where we have a shallow subcropping water table with saline sedimentation occurring in that deflation sump. Here's a similar thing here, also in the empty quarter, where you can see the efflorescent salt crust surface indicating a fairly shallow water table, a Sabkha, continental Sabkha succession in the interior of the UAE. Likewise here, in this video, we can see the same thing as we move toward the deflationary area with the salt incrustation in between the active dune systems. So once again, we can see that that very flat surface that defines the top of the capillary zone is what's controlling our Sabkha sedimentation in this particular example. We can move to a succession of paleochannel salt lakes in the Curtin Springs region of the Northern Territory in Central Australia, and we see similar associations, where in the topographic lows of the landscape we have shallow water tables in old paleochannel positions, and we have extensive salt flats or continental Sabkha associations forming in these groundwater sumps with shallow water tables. And quite often in the uppermost zone of capillary evaporation we can see ephemeral salt crusts accumulating. This particular area here is once again a hot arid desert with summer temperatures up to 47 degrees centigrade and daytime lows at around 8 to 9 degrees with around 9 inches of annual rainfall. Or we can go to Bonneville Salt Flats to the west of the Great Salt Lake. Now we're in a relatively cool arid desert system with a hot July average maximum around 33 degrees centigrade and a winter minimum around -5 and around 5 inches of annual precipitation. And once again we see this very extensive salt encrusted surface defining the top of the capillary zone within the Bonneville salt flats. And what we're also seeing here, and this is true of all of these salt flat systems, is that at times those same salt flats are covered by water, in this case rainwater, and we see the dissolution of that salt crust. And another thing that's common to all of these salt flat areas is that they are forming in zones where we're seeing deflation of the upper sediments sitting above the top of the zone of capillary wicking. So for example, around the edge of the Bonneville salt flats we see gypsum dunes made up of sediment which is blown out of the desiccated stage of the Bonneville salt flat. So this is sediment which is accumulated in the evaporating brine pans of the salt flat, and then as it desiccated we can see deflation moving that sediment into the surrounds, into the peripheral regions of our salt pan succession in the Bonneville salt flats. Or we can go to Guerrero Negro in Baja, Mexico, where there is now one of the world's largest halite manufacturing plants on the system. But once again, this is a hot, arid coastal desert. Maximum temperatures around 30-32 degrees and minimums around 7 degrees centigrade with around 4 inches of rainfall a year. And once again, we see this very extensive top of the capillary zone system of halite incrustation defining the top of capillary wicking in this succession. And in the lower parts where we see ponding of brine, we also see subaqueous evaporite deposition as well. And once again, it's a zone that is susceptible to aeolian deflation in the system. Or we can go to the east coast of Saudi Arabia, south of Dammam, Khobar, and look at the Ras Qaria or the Sabkha Adnan region, and we see the same thing. We have in the Ras Qaria region some small saline pans, but more extensively in the region of Sabkha Adnan we see this salt encrusted, very extensive flat-topped surface. On the coast, very similar to what we see on the Abu Dhabi Sabkha, we see megapolygons or tipi structures forming as cemented crusts in the intertidal sediment. Within the Sabkha, where we have local areas of brine ponding, we see well-developed capillary growth salt crusts on top of the Sabkha surface. These typically start out as subaqueous stages of pan evaporation where we have halite crusts, but then the process of halite precipitation continues and we generate into these megapolygonal, sometimes called pressure ridge or PT structures within the halite crusts themselves. But once again, we also see the evidence of deflation. So around the edges of Sabkha Adnan and eastern Saudi Arabia, we see gypsum aeolian sand dunes. And here's a section through one of these now partially eroded gypsum dunes on the edge of Sabkha Adnan. So all of our salt flats or sabkhas we can divide into three basic types. We can have coastal or marine margin sabkhas, exemplified by the modern day Abu Dhabi Sabkha. We could have sabkhas surrounding a saline pan, as we saw in Owens Lake and in Great Salt Lake. Or we can have aeolian interdunal sabkhas, as we see in the empty quarter of Saudi Arabia. There's another commonality we see to all these salt flat systems, and that is this notion of flood or fry. By that I mean that when we look at these saline systems, most of the time they're frying, they're dry, we're seeing capillary wicking, we're seeing this ephemeral halite crust forming. This is an image taken from the Dalol salt flats in Ethiopia in the Danakil Depression. But this same region, every now and again, looks like this, where we've had, after storms, we see the system covered in relatively fresh water and the halite crust dissolved. So in addition to the concept of capillary wicking and the concepts of Stokes surfaces or deflationary tops to the zone of capillary wicking, we also have to introduce this concept of flood or fry hydrologies, where most of the time they're frying, occasionally they're flooding. And so there are commonalities to capillarity of salt flats anywhere in the world. They are all characterized by flood or fry hydrologies. They're all characterized by aridity, where there's an excess of evaporation over inflow or precipitation in the succession. They're all characterized by deflation, typically with some sort of aeolian deposits in the surrounds or in the hinterland to the salt flat. They're all characterized by shallow saline water tables, and those water tables are usually within a metre or two of the surface when we see these salt-encrusted surfaces forming. And they're all part of a hydrology where they are the saline edge. The Sabkha or the salt-encrusted zone is the saline edge around what may be a more perennial part of either pan or perennial salt lake accumulations. So within the Sabkha Depositional Association, we can see that the Sabkha or the saline salt flat association tends to occupy the more elevated and generally the more peripheral parts of the groundwater sump where our evaporites are accumulating. So with those commonalities in mind, let's go back and have a look at Sabkha sedimentation and capillarity in the context of what's been observed over the past half a century in the Abu Dhabi Sabkha successions. The Abu Dhabi Sabkha makes up the supratidal portion of the coastal zone of the Trucial Coast, or the Al-Tat coastal zone of the Abu Dhabi Emirate. The original work that was done by Doug Shearman was done to the northeast of Abu Dhabi City, or Abu Dhabi Island. That area has now largely been developed. It's under airports, soccer stadiums and so on. So a lot of the hydrology has been disturbed in that region. So we'll go back and we'll look at the classic context of those papers, but then we'll test it against observations that have been done further to the west of Abu Dhabi, in the vicinity of the Sabkhas south of the Khor al Bazam lagoon, and also the sabkhas around Yas Island and Sabkha Mati. So let's go back and remind ourselves of what was in that classic Sabkha succession as documented by Doug Shearman and his various PhD students. We have a system which is, if you like, the Holy Trilogy, the peritidal association, subtidal, intertidal and supratidal, and within that anhydrite is forming above the water table in the capillary fringe, as is some gypsum, and below the water table in the intertidal and the subtidal associations we see gypsum accumulating both as layers and as large poikilotopic lenticular gypsum. Now, one of the key characters of this Sabkha association is the actual thickness of the Sabkha succession above the water table within the prograding Sabkha. This is a map from Patterson and Kinsman based on earlier work by the Imperial College group showing us the depth in centimetres to the water table in the zone that was studied via Imperial College. And you can see that throughout the supratidal Sabkha succession, the water table is between 20 and 80 centimetres below the Sabkha surface. It's always less than 1 metre. And that's a characteristic observation because that, as we discussed before, is the thickness of the zone of capillary wicking with its deflationary top. Now, if we put that in the context of the broader depositional setting, we can see that the Sabkha is the supratidal portion of what is a prograding carbonate coastal barrier lagoon system. Now, if we put that into the context of what is the relative thickness of the Sabkha succession, the figure on the right gives you an indication of the true thicknesses of the succession, and we can see that a Sabkha sequence is dominated in terms of late Pleistocene sedimentation, is actually dominated by continental Aeolian sand, overlain by Holocene intertidal sandy carbonates, quite often with preserved marine hard grounds capping and within that subtidal succession, passing up into a zone of microbial mats, algal peats, cyanobacterial peats, overlain by the supratidal anhydrite-rich succession. If we put that into the thickness context, we can see that the actual volumetric proportion of the Holocene succession, that is supratidal, is fairly thin. And in terms of the late Pleistocene succession, it's just a thin supratidal capping to this desert sand association. So Sabkha doesn't dominate in its depositional association. It is volumetrically a fairly minor part of this prograding coastal hydrology. So let's have a look at the Sabkha succession now in Abu Dhabi. And so here is the classic ephemeral halite saline pan crust capping the Sabkha succession. And here is the typical flat appearance of the Sabkha, in this case without the ephemeral halite crust developed on it. And we can see it's a quite laterally extensive flat surface. It's about 15 kilometres wide, the Holocene succession at its maximum extent. And we pass through the intertidal zone with its classic laminated and pustular microbial mats. We're looking toward the lagoon in this particular perspective. It's an image from Steve Lockyer. And we can have a look now at probably one of the best exposed trenches that was exposed during the construction of the Musafir Channel, a shipping channel excavated to join up the industrial area of Abu Dhabi with the open Gulf. And as part of that construction, large sections of the Sabkha were trenched as this channel was excavated. And they've been studied by a variety of geologists, including yours truly. And what we see, this is from a paper from Stromiger et al. Back in 2010, is this characteristic succession of the Sabkha. But this is now showing us the lateral extent of the various facies exposed within or beneath the prograding supratidal sediments. And we can see that it's a complex of tidal channel and lagoonal packstones in the subtidal association, along with some tidal bar sands as well. But in terms of the evaporite distribution, everything below the water table is gypsum in terms of evaporites. And not only that, but that gypsum is growing diagenetically in a normal to restricted marine matrix made up of muddy to sandy variety of depositional settings, and that the anhydrite forms part of the supratidal association. And that anhydrite is typically less than, or that anhydrite containing zone is typically less than half a metre to a metre thick. And volumetrically, the bulk of the sedimentation that we're seeing in the Sabkha is gypsum, not anhydrite. The anhydrite is only found in the upper sections above the water table in this association. And here we can see the lateral extent of the subtidal, the intertidal, and the supratidal zones within the Sabkha. And we can also see that within the supratidal zone that is the Sabkha, there are a whole range of outcropping mesas of Miocene sediments, as well as an interfingering relationship on the hinterland side with late Pleistocene Aeolian sediments, which also underlies, we saw earlier, the bulk of the Sabkha association. And so schematically, we can break out the Sabkha into three basic styles. The marine dominant Sabkha association, which is dominated by a carbonate matrix with the development of gypsum below the water table and gypsum anhydrite above, and then the continental portion of the Sabkha on the hinterland side of the modern prograding Sabkha, where a quartzose matrix, an Aeolian deflation-derived matrix, is dominant, but superimposed on that we have very similar patterns of evaporite sedimentation, with gypsum below the water table and a combination of gypsum and anhydrite above the water table. Also buried within the Sabkha are a series of beach ridges with typically planed off deflated tops, giving them a less obvious outcrop appearance in the Sabkha. But they're the three dominant Sabkha associations that we see. A deflated top carbonate beach ridge association acting as a local aquifer, and then the typical carbonate matrix Sabkha with gypsum below the water table and anhydrite above, or the Aeolian-fed continental dominant portion of the Sabkha. So most of the marine matrix into which our anhydrite and our gypsum is growing diagenetically, that matrix is being supplied from the lagoon on the seaward side during combinations of high tides, shamals, whereas the matrix is supplied by the hinterland by a combination of Aeolian and sheet flood transport, into which our gypsum and anhydrite can then grow via capillary wicking and capillary evaporation. And it's also interesting, and we could come back to this a little bit later, is that the Sabkha hydrology is another example of what we see in many saline salt flats around the world, including the salt lakes of Australia, Saudi Arabia, Africa, where the hydrology is decoupled, so that the uppermost portion of the hydrology, where our halite crusts are forming, is typically decoupled from the hydrology in the underlying succession. And there's a whole range of different environments where this decoupling has been documented in saline mudflats. You can have a look at chapter 2 in my book to look at the detail of some of this decoupling. But the important point is that in this context, we have to consider that the hydrology, which is supplying water to the system, may not be dominated by the same hydrology that is supplying the bulk of solutes to the system, both now and in the past. And we'll come back to this a little bit later. Let's have a look at the distribution of Sabkha anhydrites. And as we said, the general rule is anhydrite in the Abu Dhabi Sabkha is found always above the water table, often in combination with gypsum, but never below the water table, where gypsum dominates. And so here we can see that quite clearly, and also we're seeing the three dominant matrix styles into which our evaporites are accumulating here. We can see that we've got lenticular gypsum growing below the water table in buried beach ridge sediments, in lagoonal sediments, whereas anhydrite forms above the water table. And so I would draw the Sabkha succession with a slightly different set of emphases to what's been done in terms of previous interpretations of the Sabkha succession, because I think we have to emphasize the effect of capillary wicking in the Sabkha succession. So the Sabkha is centered around the water table, where we have varying combinations of algal mats and beach ridges below the water table, with gypsum accumulating, typically as poikilotopic, but sometimes as layers of gypsum as well. And then above the water table, we have a combination of intrasediment growth of both gypsum and anhydrite. And that's growing in the zone of capillary wicking, which is up to a metre thick, typically more like half a metre thick, and it's capped by a deflationary or Stokes surface, which is controlling the position of the upper part of the Sabkha. So what we're seeing in this succession is the zone of capillarity being preserved. So the Sabkha succession is made up of the saturated zone and the capillary fringe. The majority of sediment that would have sat at any time in the vadose zone without being held together by the moisture of the capillary fringe is deflated away in a Sabkha succession. And we can see that by these classic erosion surfaces. Here is a layer of enterolytic anhydrite, that's a dirham coin in there for scale, and you can quite clearly see that that folded layer of enterolytic anhydrite has been truncated. This is in a trench we dug back in the mid-80s on the Al Dabaya Sabkha to the west of Abu Dhabi. You can see that that erosion surface has growing above it a later episode of anhydrite and gypsum growth. And this relates back to the documentation of this classic deflation surface. And here are the fingers of Doug Shearman pointing out the deflation surface on the Sabkha succession to the northeast of Abu Dhabi city, as first documented back in the mid and late 1960s. And these erosion surfaces, these truncation surfaces, which are Stokes surfaces, are one of the important hydrological indicators of a Sabkha hydrology. What they're telling us is that we have a pre-existing matrix. It can be continental, it can be marine, and within that matrix, in the zone of capillary wicking and capillary evaporation, we have intrasediment growth of calcium sulfate, both as gypsum and as anhydrite. The growth of that intrasediment calcium sulfate increases the volume of the supratidal sediment. That in turn jacks up or pushes up the upper part of that zone so that it moves out of the top of the zone of capillary wicking, so it becomes totally vadose without capillary moisture, and it can then be deflated. And that's how we generate these deflationary surfaces that we see in the Sabkha. They're indicative of the capillary hydrology, where the intrasediment growth is pushing the sediment above the water, the matrix sediment above the water table, out of the top of the capillary zone, and it's being deflated off. So to identify a Sabkha in the rock record, you must always identify a deflation surface. If you don't have a deflation surface, you have no clear indication that that was a Sabkha association. The other thing to notice here is that the thickness of the supratidal or the suprawater table succession is defined by the thickness of that capillary fringe. So, within that context of intrasediment growth, what's the source of the waters that are feeding in the calcium and the sulfate into those successions above the water table? Are they marine brines? Are they continental brines? Are they coming from above, or are they coming from below? Well, we certainly know that in the Sabkha we have strong winds that move the carbonate matrix from the lagoon into the Sabkha succession. That's how the carbonate matrix gets there. We also know that on the backside we have some aeolian matrix being blown in from the backside of the Sabkha. On a diurnal basis, as we see the tides coming and going from the marine side of the Sabkha, we see an exchange of tidal waters, and this is very clearly documented in a video by Steve Lockyer. And what you're seeing here is a algal floored tidal channel where you can see that the tide is rising, and so you can see the tidal waters moving from left to right up that channel. But on the base of that channel, there's also evidence of waters moving from right to left. These are the dense hypersaline waters that have been created by evaporation on the Sabkha surface and are then returning back into the lagoon. So there's clear evidence that there is an exchange of seawater, at least in the intertidal to the lowermost supratidal zone on the Sabkha. And these types of observations led in the 1960s to the models where the Sabkha hydrology was seen one primarily of a marine recharge setup, where the bulk of the waters was being supplied by tidal flooding and then storm flooding further back onto the more distal ports of the Sabkha. There's also occasional rain recharge, but the majority of the recharge in this model was coming from the lagoon into the Sabkha. That water then sank down into the Sabkha succession, and then consequently there was evaporation and capillary evaporation, causing the precipitation of the calcium sulfate evaporites in that Sabkha succession. So earlier models back in the 1960s and throughout most of the 70s saw marine recharge as a dominant force for supplying solute into the Sabkha associations. But then when people started to do strontium isotope work, we started to see combined models being published for the Sabkha hydrology. So there were times where on the seaward side we had seawater flooding. There was a model called evaporative pumping whereby as capillary wicking occurred, the seawater was flowing laterally in the subsurface to resupply that water loss from capillary wicking from the marine side of the Sabkha. And then there was an additional model, and this was done by Judy Mackenzie and others back in the late 80s and the early 90s, where we saw the ascending brine model, where we started to get an implication that there was perhaps some other source of solute that was not purely marine but had a continental influence in the succession as well. And so Muller et al., in a paper published back in 1990, divided much of the coastal Sabkha zone into three zones: a marine side, a mixed Sabkha water side proportion, and then a landward continental water supplied Sabkha hydrology. But subsequent to that, in the late 90s, work done by Warren Woods and co-workers from the USGS came up with some rather interesting conclusions, which are still gaining acceptance amongst a range of sedimentologists, but based on very detailed physical measurements, actual measurements of the Sabkha hydrology, not inferred, but actual measurements of the Sabkha hydrology using nests of piezometers and wells. They came up with the following conclusions. The earlier conceptual model of evaporite pumping, whereby water is being replaced as it's lost by capillary wicking from a seaward supply, they concluded this model is not consistent with the fluxes they measured in their piezometer nests in the hydrologic budget. They also concluded that the seawater flooding model, the marine recharge model, or the seaward flooding reflux model, is not consistent with the results of their work, in that you can completely account for the solute budget without calling upon seawater flooding. So this is a paradigm shift in terms of the hydrology of the Abu Dhabi Sabkha. But because much of this work was published in the hydrological literature, a lot of it didn't actually enter the mainstream geologic literature, and it's still slowly gaining acceptance. So let's go back now and have a look at what Warren Woods and others did in their work in the mid and late 90s and the early 2000s in the Abu Dhabi coastal zone. They also did similar work in Saudi Arabia. So this is the Trucial Coast, the Al-Tat Coast, and this is showing you the density of the shallow piezometer nests, the solid red circles that they placed across the Sabkha, as well as some deep drill holes which intersected all the way down into the underlying tertiary succession below the Sabkha. So you can see quite clearly that this is a very rich set of data on which they based their hydrological interpretations and conclusions. And this is just showing you the wells that they completed into the tertiary succession through the Sabkha, as well as a section which we'll emphasize, which is the X prime succession, where we've got the actual thicknesses measured of the associations. And as you can see, across that X prime succession, we are looking at a system which is predominantly an aeolian sand aquifer system as we move from the landward to the seaward. And they found there were some interesting things happening based on their 450 shallow piezometer nests and their 6 deeper wells into the tertiary section, into the Sabkha west of Abu Dhabi Island. And this is what they found. On the left, we have the evaporation rates measured at Site 1 and Site 2 on the Sabkha, where you can see that on a daily basis, evaporation rates, as one would expect, are highest around midday and lowest around midnight. They also found, in terms of the depth to the water table, that there was significant recharge to the water table coming from rainwater. This is documented by piezometer nests. So the figure on the right is showing you measured rainfall versus depth to the water table. And you can see how there's been a rise in the water table of some 20 centimeters related to a rainfall event. And using that monitoring over a number of years of rainfall events, recharge rates, and piezometer nest measurements, they came to a rather interesting conclusion. If you look at a block which has a 1 meter face and a 10 kilometer length, what they found was, in terms of the water flux, because of the low permeability, and they measured the permeability of Sabkha sediments, because of the very low permeability of the Sabkha sediments are too impervious to facilitate kilometre scale lateral recharge. I'll say that again. Sabkha sediments are too impervious to facilitate kilometre scale lateral recharge, either from the seaward side or the landward side. They also measured the solute content of the waters and did a solute flux budget, and they found that more than 95% of the solutes supplying the anhydrite, the calcium and the sulfate supplying the anhydrite growth in the Sabkha came from upwelling regional groundwaters. This is not marine recharge moving laterally from the coastal zone. This is waters carried through that Aeolian aquifer from the tertiary sediments in the hinterland to where they are upwelling into the coastal zone. And where that upwelling is taking place, those sediments are accumulating anhydrite by the evaporation of regionally upwelling groundwater flows. So as I said, this is a paradigm shift in the nature of the way we see the Sabkha solute budget. Historically, it's been seen as mostly a marine-fed system, but actual measurements, piezometric and laboratory measurements of permeability show that that's not the case. The Abu Dhabi Sabkha is being supplied via upwelling of regional continental groundwaters. They are not marine-derived sediments. In terms of the water budget, most of the flux in the Sabkha is coming from rainfall, not from continental waters, not from marine waters, from rainfall, in terms of the vertical water budget. So this is some of the work they did looking at the Sabkha ionic proportions in the Sabkha and on the more continental sides, and you can see that throughout these are sodium chloride brines, and that the levels of sulfate are up there with the levels of sodium and chlorine, and that the lack of increase that we see as we concentrate a Sabkha brine, there is little or no increase of sulfate as the calcium concentration increases. And there is also, as one sees in a lot of brine systems, a pH decline as the concentration of the capillary waters and the magnesium proportion in those capillary waters increases. So pH decreases, waters become more acidic as the concentration increases. And there is definitely in this system an excess of calcium over sulfate. But the most interesting conclusion was the nature of precipitation of the Sabkha anhydrite itself. Now this is showing us the temperatures that they measured at various depths in the Sabkha. The red line is showing you a diurnal fluctuation for July the 6th, 1999, where we can see the fluctuation going from 4 o'clock a low at around 34.5 degrees at the surface up to a early afternoon high of around 37.5. So the surface temperature is fluctuating. And as we go deeper into the Sabkha, we see a similar fluctuation in temperature, but it's decreasing. The level of fluctuation is decreasing as we get deeper into the Sabkha. So we've got a depth of 15 centimeters in orange, a depth of 30 centimeters in green, and a depth of 60 centimeters in purple. And you can see that by the time we get to 60 centimeters, the Sabkha temperature is near constant on this day at around 36 degrees centigrade. So what's this got to do with the way in which anhydrite forms in the Sabkha? Well, as we discussed in an earlier module, anhydrite, like gypsum, are retrograde precipitates, which means that as the temperature increases, the solubility decreases. And so that particular retrograde salt phase is more likely to precipitate. And this chemistry I'm showing you in this image here, once again from a paper by Woods et al. In 2005, it's showing you, based on actual measurements of pore fluids in Abu Dhabi, how the anhydrite is precipitating within the capillary zone because of a temperature increase as the waters upwell through the Sabkhas and go through that transition as the temperature increases as the waters approach the surface. And so within that zone of capillary wicking, we have a situation set up where, based on the pore fluid chemistry in the Abu Dhabi Sabkha, precipitation is occurring because of a temperature increase in the pore brines in the zone of capillary wicking. In other words, calcium sulfate formation in a Sabkha is a thermalite. It's a temperature-controlled precipitation. As we heat those rising, deeply circulating continental groundwaters, and as they approach the surface due to capillary wicking, we precipitate anhydrite. And that's why the anhydrite doesn't sit at the surface like the halite, capillary evaporated halite sits at the surface, but it sits at a depth immediately above the water table. And we don't see it forming below the water table because we don't see sufficient temperature increase below the water table in the Sabkha. So, what can we now say about the hydrology that controls Sabkha sedimentation? Well, all Sabkhas, all salt flat sedimentation above the water table will be controlled by capillary wicking or capillary evaporation. where the maximum salinity will sit in the upper 5 to 10 centimetres of the capillary zone directly below a deflationary Stokes surface. Gypsum within that system can occur anywhere in the system, but it tends to be best formed in the Abu Dhabi Sabkha below or at the water table, whereas an anhydrite are found above the water table. And this leads to the conclusion, as discussed by Woods et al. In 2005, that anhydrite is most likely a retrograde thermalite mineral forming via heating in the zone of capillary evaporation. And the last conclusion is that the preservation potential of a complete modern Sabkha supratidal succession, a la Abu Dhabi, is low, because the zone of capillary wicking is controlled, its thickness is controlled by deflation. So, what are the implications of this hydrology in terms of Sabkha preservation, and the fact that Sabkha evaporites are capillary zone diagenetic sediments? Well, we must recognise in any preserved ancient succession indications of the fact that Sabkha evaporites grow in a pre-existing matrix, and they have a capping deflationary or Stokes surface, and that individual cycles within that zone, that supra-water table zone, or if you want to call it supratidal in a marine margin setting, that thickness is controlled by the height of the capillary zone. And the height of the capillary zone, with sufficient permeabilities to facilitate capillary rise, will be between 0.5 and 1 metres. Now, the other thing that's interesting to think about here is, if we look at the hydrology in a modern Sabkha succession, what happens to that thermolytic anhydrite once it's buried below the water table? We don't see that happening in the Sabkha today, but the implication would be, if we could bury a Sabkha succession below the water table, then that anhydrite should reconvert to gypsum once it subsides below the water table. Sabkha successions are part of an overall hydrology passing from the pan edge into the pan centre, and that the Sabkha or the saline salt flat sediments that we see in ancient evaporites and modern evaporites are indicative of a capillary fringe or capillary wicking mechanism of salt formation. As we go further into the Sabkha, we go into the saline pan, where we see the coming and going of surface waters, and then out into a more permanent perennial water body in the lowermost parts of the sump or in the Saltern Seaway in an ancient evaporite succession. So this has implications in terms of how do we preserve Sabkhas. Well, we're not going to preserve Sabkhas in the current modern hydrology of the Abu Dhabi Sabkha, because as the Sabkha progrades seaward, the backside of that Sabkha, the hinterland side of that Sabkha, is going to be deflated, and that supratidal proportion will be removed. And we see that on the backside of the modern Abu Dhabi Sabkha, where we have eroded portions of the backside of the Sabkha in deflationary zones back down to the level of the upper intertidal hard grounds. So this modern Abu Dhabi Sabkha is a self-cannibalizing system. How do we preserve it? Well, we can only preserve it if we have an aggrading brine sump hydrology. In other words, we're not going to preserve it in the modern hydrologies, but if we have ancient hydrologies as we form in basin-wide or platform evaporite systems where we have a transgressive, not a retrogradational brine system, but a transgressive brining system which is brining upwards and spreading out laterally, then we have the potential where we basically encase our Sabkha sediments in later hypersaline brine sediments. As we bury the succession, we can preserve Sabkha associations. But we'll have both modern and ancient quite low preservation potential of any Sabkha succession if it's prograding, rather than being a brining upwards transgressive hydrology. So we then have to ask ourselves the question, if we make a Sabkha interpretation in an ancient succession, is it likely to be the dominant explanation of a thick succession of pure ancient nodular anhydrite? And the answer is probably not. We need matrix rich for a nodular anhydrite to form, and if it's a prograding succession, as in a typical peritidal association, we probably won't preserve much of the supratidal Sabkha association. And in fact, most ancient Sabkhas are probably not peritidal. Most ancient Sabkhas are probably strandzone deposits about hydrographically isolated transgressing evaporite brine sump systems. And then another question, and we'll address this in another module, is how much of the nodular anhydrite we see sitting within what are matrices indicative of normal marine or fluvial or aeolian sedimentation is actually a depositional or a syndepositional Sabkha product versus a diagenetic brine crossflow deposit. And we'll address that in another module when we look at the shallow burial hydrology and the nature of brine reflux in ancient evaporate depositional systems.